This session is on reversible reactions and dynamic equilibrium. It sounds complicated, but it's actually quite easy if you listen to all the information in this video. By the end of today's session, you'll be able to define what a reversible reaction is, what a closed system is, and we'll be able to look at dynamic equilibrium. We'll also use Le Chatelier's principle to work out the ideal conditions for a given reaction. In this case, we're going to look at the Haber process reaction. A reversible reaction is shown by this arrow here, where one arrow is going forward and another one is going backwards. The definition for a reversible reaction is one in which the products can turn back into the reactants without any loss or gain in mass. Closed systems are a key condition for dynamic equilibrium. A closed system is one in which the reactants cannot be added or escape. We can only change the conditions outside, things like pressure and temperature. In this reaction here, hydrated copper sulfate would be turned into anhydrous copper sulfate and water. The reverse reaction would also happen. This will happen constantly because it's closed conditions, this closed system. Nothing can escape or be added. A dynamic equilibrium is when both the forward and backward reaction happen at the same time and at the same rate. Now it's called a dynamic equilibrium because the position of the equilibrium can move in favor of the forward reaction or the backward reaction based on conditions. If the line moves to the right, it favors the forward reaction. If the line moves to the left, it favors the backward reaction. Every time it moves forward, more products are created. Every time it moves backwards, more reactants are created. I mentioned before that we can change the pressure and temperature and have an effect on a closed system. A scientist called Henri Le Chatelier had a principle whereby everything in nature wants balance. So if we increase the temperature of a reaction and it's already exothermic, nature will want to counter the reaction by lowering the temperature. But the Haber process equation is one that we look at often when we look at Le Chatelier's principle. When we look at the pressure, we need to look at number of molecules. So it's all to do with the number of molecules of reactants and the number of molecules of products. Now, there's one molecule of nitrogen here. There are 3 molecules of hydrogen here. This number before any element or compound will tell you how many molecules of that element or compound there are. Okay? If we look over the other side, we've only got 2 molecules of ammonia. Le Chatelier's principle, an increase in pressure always favors the side with the least amount of molecules. A decrease in pressure does the opposite, so it will favor the side with the most molecules. The Haber process equation, if we increase the pressure, it will favor the side with the least amount of molecules. So we will produce more ammonia, the equilibrium will shift to the right. To use Le Chatelier's principle with temperature, we need to first identify whether the reaction are endothermic or exothermic. In this case, the forward reaction is exothermic, so the reverse must be endothermic. This is the same case in any reaction. If the forward is exo, the reverse will be endo. If the forward is endo, the reverse would be exo. We then look at Le Chatelier's principle. An increase in temperature favors the endothermic reaction. Because this reaction is already letting out heat, if we add more heat in, nature will want to balance the temperature change. So it will move it towards the left and favors the endothermic reaction. If we decrease the temperature, the exothermic reaction will be favored. So ideally for the Haber process, an increase in temperature is not good. We need to decrease the temperature to get more ammonia. Now the Haber process equation is really common in exams. What you need to do first is pick out information from the question or things that you already know about this process. So we can add on the things that we already knew, like it's an exothermic reaction going forwards, there's 2 product molecules, 4 reactant molecules. The next thing you would do is create a grid like this. It will really help you in the exam. Then you bullet point what would happen to equilibrium position when an increase in temperature occurs, a decrease in temperature, increase in pressure, or decrease in pressure. Now, you only technically need to know 3 points, and then the other 3 points will be opposite. Okay? So, if we increase the temperature, equilibrium moves to the left. It favors the endothermic reaction, the lower yield of product. Now, yield is the amount of desired product. From this reaction, we want to create ammonia. Okay? If we increase the temperature, we won't create much ammonia. So the ideal condition would be to decrease the temperature because equilibrium will move to the right, over to this side. It will favor the exothermic reaction. You have to talk about that in the exam. You'll have a higher yield of product. Over to the pressure side. If we increase the pressure, remember equilibrium will move to the right because there's less molecules on this side. We'll have a higher yield of product. If we decrease the pressure, the opposite will happen. Equilibrium will move to the left. It will favor the side with the most molecules. There's more molecules on this side, so more reactant molecules will be produced. There's a lower yield of product. Therefore, the ideal conditions for the Haber process are high pressure and low temperature. These do have their problems, and we'll go into that in the video on the Haber process